As a reminder for proofs, write out every single step in words and in math notation. Whenever you have to prove that something equals something else, don't ever work across this equal sign. Don't add or subtract or divide. Think of it as this is your problem and this is your answer. And then here were some of the hints we talked about last time. Let's simplify things by distributing and combining like terms, or if you have fractions, you may want to factor and cancel things. It also helps to convert everything to sines and cosines because we know how to convert everything to sines and cosines, and that will help you with this next new hint, look for identities. You should be aware of all of these identities at this point, how to convert to sines and cosines, the Pythagorean identity, and the sum and difference identities. We are going to specifically be focusing on these identities in proofs today. And you also will need to have a unit circle handy, so take a minute to write that out or print it off. And let's get to it. All right, example 1. We want to prove that sine of theta minus beta times cosine beta plus cosine of theta minus beta times sine beta equals sine theta. So all of that is going to simplify. All right, so the first thing I see is that I have stuff being added, angles being added together. So let's use this identity to break it all down to just sine thetas and cosine thetas, sine alphas and cosine alphas, and get rid of this plus that's going on in our parentheses. That's just a lot. So we are going to use the sum and difference identities here. To rewrite, I am going to rewrite this using my identity. Since there's a minus between them, I want to put a minus between these two. I put this in parentheses because I am reminded that I am multiplying all of this by cosine beta. All right, I am also going to replace this one. I probably won't have space to do that. So I'm going to replace this cosine theta minus beta with this identity here. I am subtracting the angles, so I will add, red and red, add my pieces together. And reminder, we only work on one side of the proof, so I'm going to just work on the left-hand side and get it to simplify to sine theta. Okay, now that I have that, I hate parentheses. We need to simplify this. It may not look simpler to you, but it is simpler to every mathematician if we get rid of parentheses. So let's simplify this. What I mean is I'm going to distribute my cosine beta and I'm going to distribute my sine beta. So one way to simplify is to distribute and combine like terms. So distribute or do algebra here to get all right, so it looks messier, but actually, as I was writing this, I noticed I have two pieces here that have a sine beta, a cosine theta, and a cosine beta in them. Yes, they're written in a different order, but that doesn't matter. These are all written to one well, none of these have exponents on them, and it's all a sine beta, a cosine theta, and a cosine beta. So these are like terms. When we distribute, we try to distribute so then we can combine like terms. So I can add these two together. I have a negative sine beta, cosine beta piece, and I have a positive sine beta, cosine beta piece. So if I add these two together, I would call that adding or combining like terms, or you can just say algebra. If I add these two together, they happen to add up to 0, which is super convenient for us. All right, now I'm stuck. What's going on? I haven't mentioned this in a hint, but you may have noticed, I have mentioned this before, if you have sine squareds and cosine squareds, you want to try and figure out if there's a way to use the Pythagorean identity. So notice I have a cosine squared beta and a sine squared beta, and they both have a sine theta with them. So I can factor or use algebra to pull that sine theta out front, and then I'll be left with the Pythagorean identity. I'm not going to write all that out because that's a lot of words. Cosine squared plus sine squared, as long as they have the same angle and I'm adding them, is just 1. And so sine theta times 1 is sine theta, which is what we are trying to get to. So we're done. We did it. Reminder, you don't have to necessarily follow these same steps that I did. You can work this out in a different way as long as you use legitimate math and you show every step. You should be able to still get my same answer. Let's do another example. All right, I'm going to start this one the exact same way before. I am going to replace both of these with their sum and difference identity. This is the same thing, except they're using x's and y's instead of thetas and alphas. The first one is a plus. So I will put a plus between and the second one is a minus. So I need to put a minus between. I first started to write my parentheses here just to make it super clear this was from here and this was from here, but I realized the parentheses are important because I'm subtracting this second identity. I'm subtracting it. So I need to distribute before I can actually get rid of these parentheses. So distribute or do some algebra to get rid of your parentheses. Now what? Notice I have a sine x and a cosine y piece. I have two sine x cosine y pieces. So let's add those together. So combine like terms, add, do algebra. I want to add these two pieces together. So 1 minus 1, they add to 0. Oh, and if I had just looked ahead, I should have also realized you could have technically done this in the same step, but it's better to do everything in every little piece. These two are the exact same thing as well. They both are sine y and cosine x's. So again, I can add these two together, combine like terms. I have 1 sine x, I have 1 sine y cosine x and 1 sine y cosine x. So when I add them together, that means I have 2 sine y cosine x's, which is what I'm trying to get in my final answer. So I am finished. All right, let's do a couple of problems where you need a unit circle. It's going to be the same exact idea, but instead of x's and y's, I'm going to give you a number here for one of these angles. Let's actually start with this one. Maybe. We'll see how it goes. Okay, let's start with this one. All right, I am going to start the same way as I did before. I want to replace these with their sum and difference identities. I am using x's and pi over 4 instead of thetas and alphas. Plus, so that is also a plus. Minus, so this is a minus. All right, in this case, the parentheses don't matter. I did them to make it super clear which piece comes with which piece. But the parentheses aren't important. I can erase them and it'll be the exact same thing because there's that plus sign there. I don't have to distribute a positive because everything, you only distribute negatives or if there had been a number or squaring or anything like that. So here we go. All right, now let's see, what do we have going on? I have a sine x and a cosine pi over 4 piece. So I have two of those. So let's add those two together. Add. All right, so I'm adding these two. I have 1 sine x cosine pi fourth and 1 sine x cosine pi fourths. So let's add those together to get 2 sine x cosine pi fourths. And you could do this in the exact same step, but I like to do everything in its own separate steps. Notice, again, I have like terms that I can add together. I have a sine pi fourth and a cosine x piece. So again, I can add or combine like terms, these two together. So 1 sine pi fourth cosine x minus 1 sine pi fourth cosine x. This is going to cancel out. It adds up to 0. All right, so do as much simplifying as you can, leaving the generic pi fourth in there. But now we are given an actual angle here. So we can use our unit circle to figure out replace this with its unit circle fraction or with its actual cosine fraction. What is cosine of pi fourths? If you don't have that memorized straight up, then look at your unit circle. Remember, coordinate points are written cosine sine. So at pi fourths, the cosine fraction is square root 2 over 2. So I don't know what wording Alex is going to use for this. I am just going to say use your unit circle or replace it with its unit circle value. That's probably a better description. Replace with the unit circle value. So I have 2 sine x, and I replaced all of that with square root 2 over 2. And I can extend my fraction bar just to include all of this because there's no plus or minuses here. It's implied to be multiplying. And if you do that, if you extend the fraction bar, maybe it's clear for you to see I have a 2 on top and a 2 on bottom, so I can cancel those and end up with sine x times square root 2, or it doesn't really matter when you're just multiplying if you switch the order. So sine x times square root 2 is the same thing as square root 2 times sine x, which is what we are trying to get to. That's our goal. So we did it. So same exact process, it's just once we have it simplified, I can take it a step further by using my unit circle fractions. All right, let's do one last example. This time we're going to use the tangent identity. We don't use that one very often, but it is one that you should be able to apply. All right, I am going to use, there's a minus sign there, so I want to use all of these red signs. And it is 2 pi and x instead of theta and alpha. So I'm going to replace all of this with its entire identity. Okay, well that didn't get us anywhere that was helpful. So let's go on and use our new trick. This is an actual angle here, so let's replace these with their unit circle values. All right, well, what is tangent of 2 pi? All right, reminder, tangent is sine over cosine, which we have done to death in these proofs, so hopefully you know that by now. So if you take your unit circle, you need to take your x, the sine value, and divide it by your y, your cosine value, to get the tangent. And I already wrote them all around the edge in green. So 2 pi is the same thing as 0, or it's in the same position as 0 radians. So the tangent value at 0 radians, or 2 pi radians, is 0, which is very convenient for us because now I can replace that with a 0. 0 minus tangent x is negative tan x on top. And 0 times tan x is 0, so 1 plus 0 is just 1. We don't usually write things over 1. We usually just write them as what was in the numerator. So, wow, that ended up being really fast, and I was worried this one would be tricky, but we got it. So anyhow, hopefully this made sense to you. We're just using our identities and working through them and adding it on top of the other skills we know.